Alright, well, I guess I will read this too. Analog to digital converter with computation. The analog to digital converter ADC with computation module ADCC in Microchip's latest family of 8-bit MCUs has a built-in computational feature that provides post-processing functions such as oversampling, averaging, and low-pass filtering. Positive reference, ADC, conversion clock, input, trigger, negative reference, ADC result, computation. The analog input channel sources are multiplexed into a single sample and hold circuit. The output of the sample and hold circuit is connected to the converter, which generates a binary representation of the analog input. When the ADC is operating with computational features, the conversion result will be passed onto the computational feature block for post-processing. The post-processing result is then evaluated using error calculation and threshold comparison. Channel selection source. The ADCC channel selection ADPCH register determines which channel is connected to the sample and hold circuit. Channel selection sources are not limited to external analog input sources, but can also be an output of a peripheral or an internal reference voltage. Voltage reference source. The voltage reference sets the input voltage range of the ADC. It can be an external source from the VREF plus minus pins, VDD, FVR, and VSS. Conversion clock source. The conversion clock has multiple sources, either from the main oscillator, which is divided into multiples of 2, i.e. 2, 4, or 128, or from the dedicated internal resistance capacitance RC clock. Auto-conversion trigger source. The auto-conversion trigger allows the module to schedule acquisition and conversion sequences without software intervention. When a rising edge of the selected source occurs, the ADC conversion status ADGO bit is set. The sources for the conversion trigger can be found on the device data sheet for the device you are using. In an application, these auto-conversion trigger sources can be used to set the sampling period of the ADC. Operational modes. Below are the various modes available. Many of the descriptions include an image that visually describes the mode's operation along with an MPLAB code configurator screenshot indicating how the mode is easily set up. After each mode is completed, a threshold comparison is performed. Basic mode. The basic mode of the ADCC mimics the legacy ADC operation. With the auto-trigger feature of the module, input sampling can be easily triggered in the software or by other peripherals and external sources. The result of the conversion can be compared to a threshold set point, which may trigger the analog to digital converter interrupt flag. Accumulate mode. In the accumulate mode, the digital representation of the analog input signal in the 10-bit, 12-bit register. In the accumulate mode, the digital representation of the analog input signal in the 10-bit, 12-bit register ADC result high-low AD-/AD-RESL register is accumulated to the 16-bit ADC accumulator register ADACC register. With each sample, the ADC conversion counter ADCNT register is incremented, indicating the number of samples accumulated. The accumulated value can be right-shifted up to 6 times by changing the value of the ADC accumulate calculation right shift select ADCRS bits of the ADC control register to ADCON2 register. This means that the accumulated value is effectively divided by a factor of 2 ADCRS. The result of the shifted accumulated value is stored in the ADC filter ADFLTR register. Trigger convert input conversion completed. Add conversion result to accumulated value. Shift accumulated value by right shift settings in MCC and store as filtered value. I guess this is going 1, 2, 1, 2, 3. I don't know. I'm just going to follow the flowchart. Calculate error value as per MCC settings. Compare error value with threshold value as per MCC settings. Done. Threshold condition is true. And then it has the computation feature, error calculation, fixed value versus set point. Set point 0 is less than or equal to 0, less than or equal to 6,500, whatever that number, 65,535. Lower threshold, less than or equal to 100. Upper threshold, less than or equal to 250. Repeat, 0. Accumulate right shift 2. Averaging mode. The average mode is like an accumulate mode, wherein the ADACC accumulates the data sample and the ADCNT increments with each sample, except that the number of samples being accumulated in this mode is up to the value set in the AD repeat setting, ADRPT register. When the ADCNT is equal to ADRPT, the value stored in the ADFLTR becomes the average value of the input signal. This mode can be used when a defined time interval is needed for each sample. Convert input. Add conversion result to accumulated value. Number of conversion equal MCC repeat value? Question. If yes, go this way. If no, go this way. If no, then it's done. If yes, right shift accumulated value as per MCC settings and store as filter value. Calculate error based on MCC settings and compare with threshold as per MCC settings. Clear accumulated value and done. Or then I guess it's an or, and then it goes up to this stuff. I won't read this out again. Burst mode. Burst average mode. Like averaging mode, the burst average mode averages the input signal, except that the sampling is repeated quickly after a single trigger. This means that in a single conversion, all the data samples are accumulated up to the set ADRPT, and when the ADCNT matches the ADPRT value, the average value of the input signal is attained. Trigger, clear accumulated value, convert input, conversion completed, add conversion result to accumulated value, no, or number of conversion equals MCC repeat value, question. If no, goes back to the convert input. If number of conversion equals MCC repeat value is yes, right shift accumulated value as per MCC settings and store as filter value. Then calculate error based on MCC settings and compare with threshold as per MCC settings. Done. Or then go that way. Alright, I got interrupted uploading my last video. Okay, I think I read all this stuff. Low pass filter mode. The low pass filter mode acts similarly to the average mode in how it handles samples, accumulates samples until ADCNT value is greater than or equal to ADRPT, then triggers threshold comparison, but instead of a simple average, it performs a low-pass filter operation on all of the samples, reducing the effect of high-frequency noise on the average, then performs a threshold comparison on the results. In this mode, the ADCRS bits determine the cutoff frequency of the low-pass filter. With each trigger, the ADC conversion result is sent through a filter. When ADRPT samples have occurred, a threshold test is performed. Every trigger after that, the ADC conversion result is sent through the filter and another threshold test is performed. Trigger, convert input, conversion completed, low pass filter, number of conversions equals MCC repeat value, yes or no. If no, done. If yes, right shift accumulated value as per MCC settings and store as filter value. Calculate error based on MCC settings and compare with threshold as per MCC settings, clear accumulated value. ADCC output actions. Threshold comparison. The post-processing result of the ADCC module can be compared to the threshold value set in the ADC error calculation mode select bits ADCalc of the ADC threshold ADCon3 register. The calculated result is stored in the ADC calculation error ADERR register, which can be compared to the selected upper and lower threshold. These two threshold values can be set by changing the ADC upper threshold ADUF registers and the ADC lower threshold ADLTH registers. A result of true based on the comparison will trigger an interrupt. Continuous mode retrigger. Enabling the continuous mode allows an automatic sampling retrigger after the threshold has been tested. In this mode, the ADGO of the ADC control 0, ADCON 0 register remains set until the threshold conditions are met according to the selected threshold interrupt mode select bits, ADTMD, and the AD stop on interrupt ADSOI and the ADCON 3.